So thanks for inviting me. I'm going to start very, very slowly, and then I'll move more towards the modern stuff as we get going. So basically, the way I think about the most fundamental questions in ergodic theory to me are as follows. So given a point in a space with some type of map that maps the space to myself, a question you might ask is, to what extent, if any, do the orbits of a generic point under this type of map equidistribute? So this is a very informal question, because how do you measure equidistribution, a priori? But you can sort of get a flavor for what's going on with some examples. So the first example is familiar to anyone who's done Fourier analysis. It basically says that if you're on the torus, your transformation is given by the point transformation, just an irrational rotation. Then you can integrate continuous functions by approximating the spatial average by these type of Jazaro sums, where in this particular case, Tnx is just x minus n alpha mod 1. So the second example concerns, again, the same space of 0, 1. In this case, T is the doubling map. It maps x to 2x mod 1. And in this case, the conclusion is that when I choose the function 0 to a half, these Jazaro averages converge to the integral of 0 to a half, namely just a half. So why do we care about this? Well, if we represent x in its binary expansion, and we say that the limit of the ENs is epsilon n to 0, just to make this binary expansion unique, then the statement that Tnx is in 0 to a half is equivalent to the statement that En plus 1 is 0. So the conclusion of this equidistribution property is that for almost every x, about half of the indices less than n are both 0 valued and 1 valued. So there's some type of equidistribution phenomenon when you take into account the binary expansion. And this property is known as normality. So to make this type of discussion of equidistribution rigorous, for the rest of the talk, we're going to impose measure theoretic structure. So for the rest of the talk, x mu t will be a probability system with a measure preserving transformation. And as usual, I define Tn f of x to be the function that starts with x, applies Tn times, and then evaluates at f. So in our previous two examples, our probability space was just the torus with Lebesgue measure, and our measure preserving transformations T were either in rational rotation or the doubling map, both of which preserve measure. So as I understand it, ergodic theory is the study of the dynamics of functions defined on X under the action of these measure preserving transformations. So the classical objects of study, as we've sort of seen, are these Jazaro averages. And the question is to what extent, if any, these Jazaro averages converge. So in the first example, we saw some uniform convergence. In the second example, we saw pointwise almost everywhere convergence. And for the rest of this talk, I'm just going to restrict, for the most part, to the Hilbert space setting. So unless I say otherwise, every function that I introduce will be square integrable. And I'll put some further restrictions on them as we need. But everything for the most of this talk is just going to be Hilbert space. So there are two types of convergence that we consider. Case one, we view these Jazaro averages as a sequence of vectors, and we sort of seek to understand to the extent to which there's some limiting vector to which these sequence of vectors converge. And then the second type of convergence is pointwise convergence, in which case one picks a physical location, evaluates these averages at that physical location, and seeks to do some limiting behavior pointwise. And the two classical ergodic theorems, due to von Neumann and Birkhoff, dictate that these Jazaro averages converge both in norm and pointwise. So I'm going to be talking about pointwise convergence. Norm convergence is much better understood at this point. So for instance, only a very little bit of Hilbert space orthogonality reasoning is required to prove norm convergence of these types of polynomial ergodic averages. So in the standard Jazaro averages, this polynomial P is the identity. So I'm just looking at the average of T and F in N. But using only a little bit more technology, one can prove that you have a similar norm convergence result for more general polynomial orbits. So the linear theory is not so exciting in the norm convergence setting, but once you switch from one function to multiple functions, the difficulty increases a lot. So the departure point for modern multiple ergodic theory is Furstenberg's proof of Semiretti's theorem, which I'll state as follows. So suppose I take a subset of the integers that's fairly big in the sense that I occupy a positive proportion of some family of intervals which increase to infinity. So I have positive relative density inside of some increasing family of intervals. And the conclusion is that for any k greater than 2, there exist infinitely many progressions, x minus n, x minus 2n, etc., that all live inside my set E. And the k equals 2 case involving 3 APs is due to Roth. So using a transfer mechanism from ergodic theory, Furstenberg deduced Semiretti's theorem from a dynamical systems result, which is slightly weaker than the below formulation, but very, very similar. So the statement is that for any bounded function, and any k at least 1, if I look at this product, T and F, T2 and F, all the way up to Tk and F, this product is bounded. So if I average an n, I stay bounded. So for each capital N, I get a bounded function. Since I'm on a probability space, bounded functions are L2 vectors. So for any bounded function, if I form these multiple Cesaro averages, I get a sequence of L2 vectors that are bounded. And if I sort of squint at these averages and just view them from the vectorial standpoint, there's some L2 vector to which these averages converge in norm. So I don't know what's going on pointwise, but if I squint at these averages, I can deduce some type of asymptotic limiting behavior. Now, almost 20 years after Furstenberg's ergodic theoretic proof of Semiretti's theorem,
Yeah, Ben, I have a question. Can you go to previous slide?
Yeah.
Not but remark. Strictly speaking, this is not Semiretti's theorem.
It's Semiretti's theorem is that there's the lim inf is non-zero.
No. Let me finish. Strictly speaking, Semiretti's theorem is about positivity of such things. The mere convergence doesn't give you Semiretti. So there are two issues here. One is convergence, and that's what you are interested in, and that's okay. But Semiretti itself is about positivity of potentially weaker modes of convergence. So unless you have positive, you don't have any Semiretti.
Yeah, that's fair enough. Let me go through that more honestly. So what Furstenberg proved is that if f is a non-trivial function, the lim inf of these averages is also non-trivial. Host and Krause and Leibman proved that in fact.
Okay, it's the positivity which matters. It's not. So you take f to be non-negative, indeed positive if you want, and then you want this limit to be positive. That's what makes Semiretti. Otherwise, it's about interesting to consider convergence itself. But Semiretti and Furstenberg Semiretti is about positivity. Okay.
Yeah, fair, totally fair.
He's right.
Yeah, this is selling Semiretti short. Fair enough. Yeah, so there's two parts. One is to deduce that this type of limit exists, and then the second is to show that you can't lose mass. That if you start with a non-trivial non-negative function, then the limit is non-trivial. That you can't lose mass in the limit, or you can't lose all your mass in the limit. So what Furstenberg proved is that the limit of these types of averages stays positive whenever f is positive, and then Hoskrah and Liebman proved this convergence result, which relies on the non-trivial limit of Furstenberg to imply the correspondence principle. Using a similar type of mechanism, again, first proving a non-negativity result and then a limiting result. In '96, Furstenberg and Weiss proved that these sequence of bilinear averages where instead of shifting linearly in the second entry, you shift polynomially. These averages converge in L2 as well. So once again, I start with two bounded functions fg, then Bn of fg is bounded as well. So it's an L2 vector. I have a sequence of L2 vectors. And if I squint a little bit at the sequence of L2 vectors, I can deduce a limiting vector to which they converge. And analogous to Semiretti's theorem, by a transference argument, you can deduce the following type of nonlinear Roth corollary. So again, you start with a subset of the integers that's fairly big. I occupy a positive proportion of a sequence of intervals that extends to infinity. And the conclusion is that there exist infinitely many nonlinear three-term progressions, x minus n, and x minus n squared, that all live inside your set. And this result admits really dramatic extensions. The most robust of which is due to Miguel Walsh, which says that, if you have any degree of multilinearity, any collection of polynomials, and any collection of transformations, which don't even need to commute, but as long as they generate a nilpotent group of transformations, you still prove a norm convergence result for this collection of averages. So in particular, if you take m-bounded functions, you form the product and the average. This average stays bounded. It's an L infinity function, so you can view it as an L2 vector. And if you look at this sequence of vectors, there's some vector to which they converge, again, in this sort of squinty vectorial sense. And the pointwise convergence story is really different. We know a lot less. So before COVID, basically all we knew about pointwise convergence in the multiple ergodic setting was due to Bourgain in the early 90s, quantitatively strengthened by Michael Lacey in the early 2000s. But the statement is as follows. Suppose I take a function that's two functions f and g they're not quite integrable, but they're just slightly better than integrable. So they have almost as bad singularities as you could hope for, but not quite that bad. But if you dictate that their product is a little bit better than L2 thirds, then the bilinear averages TNF, K, and G converge pointwise almost everywhere for, well, the interesting case is when K is not 0 or 1. So Bourgain proved this result first when F and G are bounded, and then Michael Lacey extended to the case when FG is in L2 thirds plus epsilon. And this was, if you compare this to Miguel Walsh's theorem, which concerns multilinear averages in this level of generality, we know very, very little about pointwise convergence. This is a theorem about bilinear, it's a theorem about bilinear averages in which both shifts are linear. So it's much, much weaker than what Miguel Walsh did in the norm convergence setting. But our plan is to try to generalize Walsh's theorem to the pointwise setting. So the long-term goal is to prove that whenever you have m polynomials with integer coefficients and m bounded functions and m commuting measure preserving transformations, so you relax nilpotent a bit, what you'd like to prove is that these Cesaro averages converge pointwise almost everywhere. So Walsh proved that if you squint at all of these and you view these as vectors, then you have norm convergence. What we'd like to prove is that you actually have pointwise convergence too. So the work that I'll talk about today is joint with Mirek and Tao. And we proved a pointwise convergence result in the bilinear setting. So in this setting, Bn of Fg, in the special case where P is linear, we have Bourgain and Michael's work. So we're interested in the case where our polynomials have degree at least 2. F and G they're a little bit better than integrable. And we dictate that Fg, they're not in L2 thirds, but we can relax the integrability restriction on Fg. And we can say that as long as Fg has singularities that are not terrible, then the bilinear averages converge pointwise almost everywhere. So as long as F doesn't blow up too rapidly, G doesn't blow up too rapidly, and the product of Fg doesn't blow up rapidly, then you have pointwise convergence of the associated bilinear ergodic averages. So to put this result in perspective, It's sort of useful to present a combinatorial consequence and to compare it with the work of Furstenberg. So to start, suppose I take a subset of the first n integers that's random with density delta. So you sort of randomly select delta n points from the first n integers. So if we really imagine that we had full randomness, then from any vantage point x and e, you sort of expect e to behave randomly with respect to sampling along the parabola, in the sense that the probability that x minus n and x minus n squared are both simultaneously in your set E is given by the product of the probabilities, which in this case is delta times delta. So if you average this over times that aren't too big, the average number of times less than p, so that x minus n and x minus n squared are both in your set, is like delta squared. So if E were a random set, this is sort of what you'd expect. That if you randomly sample a point in your set along a parabola, you expect that the expected number of incidences should scale like the density squared. So there's no reason why a general set of density delta should be random. So there's an obvious arithmetic obstruction. Your set could live entirely inside of a coset. But really, as far as random sampling along a parabola, this is sort of the only obstruction. So if you rule out this arithmetic obstruction, your set E does behave randomly with respect to sampling along a parabola. So what do I mean by that? Suppose I take a subset of positive upper density. Furstenberg-Weiss says that there exist infinitely many progressions x minus n squared in your set. And what we can do is we can sort of localize this result. So for any set of density delta and any epsilon that's very, very tiny, there exists a conjugacy class, z mod q. Q depends on delta and epsilon. So that for any sufficiently large time, there exists a single vantage point so that the percentage of time where x minus qn and x minus q squared n squared is in your set, it's not quite delta squared, but it's delta squared minus epsilon. And you hold in this lower bound holds uniformly for all large scales. So there exists a single physical location x, r, and e, so that you have lots of configurations xr minus n squared that also live inside your set. And if you're willing to pass to an arithmetic progression, you get the density predicted amount. Does that make sense? Nonlinear Roth is an existential statement about infinitely many nonlinear Roth progressions. Our result quantifies this and localizes this once you allow for the one obvious arithmetic obstruction. Okay. So before I turn to the main theorem, there's sort of two cases that you have to understand first, namely when one of the two functions is constant. So in the first case, if I specialize the second function to be constant, I get the usual Cesaro averages. And if I specialize the first function to be constant, I get these quadratic averages, which were first considered by Bourgain in the late 80s. And indeed, Birkhoff's theorem is that the Cesaro averages converge almost everywhere. And again, in the late 80s, early 90s, Bourgain proved that the quadratic averages converge almost everywhere as well. So an important perspective that Bourgain brought to his work on pointwise convergence was one of quantification. So pointwise convergence a priori is qualitative. There's no particular rate on pointwise convergence that's uniform. But it's really, really helpful for dynamical systems argument to be able to measure quantitatively how much a sequence of averages oscillates. So with that in mind, given a sequence of scalars an, we can detect convergence if for every altitude t, there are only finitely many times n0, n1, etc., so that the sequence of ans jumps by t. So If I have a sequence of scalars that does not converge, then there's some small threshold, so that my sequence oscillates infinitely often by over that threshold. So the contrapositive is that the sequence converges if for every small altitude, the sequence hops only by finitely many times over that altitude. So to count this, we extract the largest subsequence, n0 less than n1, et cetera, up to nk, so that ani minus ani minus 1 is bigger than t, and so that k is maximal. And we define this largest, we let nt of an denote this largest k. So the statement that nt of an is k means that there's some sequence of times n0 up to nk, so that ani minus 1 is bigger than t, but you can't find any larger subsequence. So this captures the amount of fluctuation over altitudes t that your sequence makes. And the statement that Fn convergence almost everywhere is equivalent to the almost everywhere convergence of the map that sends x to the jump counting function at altitude t of the sequence Fn of x. So the idea is that for every x, I evaluate Fn at the point x. So I get a sequence of scalars, Fn of x, and I count how many times the sequence of scalars oscillates by or jumps by an altitude of t. And Bourgain's idea was to prove a norm estimate on these functions, which would in particular force almost everywhere convergence. So this is a technique that appears in martingale theory, and the goal, following the probabilistic history of the problem, is to prove some type of quantitative estimate that the average number of times that a sequence of the sequence of averages oscillates by t scales polynomially in t. That if I take an L2 normalized function in an L2 average sense, the number of times that the Cesaro averages fluctuate by t scales like t to the negative r. So that's the goal. So there's a big difference between NT-Cn of f being finite, which is what guarantees convergence, and this type of quantitative rate, which guarantees convergence at a polynomial rate. But these types of estimates, when you think of R as being sufficiently large, are not much stronger than the qualitative formulation as well. So you're not giving up too much. And indeed, Bourgain proved the following, that for every R bigger than 2 and any altitude t, in an L2 average sense, the Cesaro averages oscillate by t to the negative r, or jump by t to the negative r. And in 2014, I proved the same result for the sequence of quadratic averages, which is something that Bourgain knew himself. It wasn't too novel. But the upshot is that for a general x, if I look at the number of times that the sequences of averages oscillate by t, this is bounded by t to the negative r. So how do you go about proving something like this? So I haven't said anything about x. I haven't given you metric structure, topological structure, differentiable structure. But what I have told you is that we're dealing with z actions, that I have a map that goes from n to tnf of x. And by a principle of Calderon, this tells the whole story, that if you have a z action, it's enough to sort of study it on z. So by this sort of principle of Calderon, if you're interested in proving this estimate at the top of the slide for a general x, it's enough to prove the estimate at the bottom of the slide for the single sequence space setting. So our measure preserving system is the integers with counting measure and a shift. And this forms a toy model, or it's sort of the toy model for all of these abstract jump counting issues. And then the same is true when I replace n with n squared and consider the dn's. So just to summarize, this is all stuff that Bourgain came up with. We started with a problem in pointwise convergence and reduced it to a problem involving proving an estimate for harmonic analytic operators over Z. So to get there, we tried to prove a pointwise convergence statement. We recast it and reduced matters to showing that a certain jump counting function converged. We planned to show that it converged by proving a norm estimate, and we transferred this norm estimate to the sequence space setting. So the upshot of all of this is that to prove a pointwise convergence result in dynamical systems, it's enough to prove a norm estimate in the sequence space setting of L2 of the integers. Okay. So in our goal to estimate the Cesaro averages, we can borrow heavily from Euclidean real analysis, which combines a little bit of probability theory and a little bit of Fourier analysis to establish the equivalent estimate, where I replace the discrete sum with an integral. I replace the discrete variable n with a continuous variable t. I replace z with r, but otherwise the two formulations are the same. In this analogy, the key to this analogy is that the orbits over which we sum have very similar traces. So if I look at the sequence of integers n greater than 1, and I just take the Minkowski sum with a unit interval, I get the sequence t greater than 1 inside of R. So I can go backwards and forwards between the discrete orbit at the top of the screen and the continuous orbit in the middle of the screen because of this sum set behavior. But if we try the same thing with the squares, we run into a geometric problem. Namely that from the perspective of density, the sequence of squares sort of acts half-dimensionally. In the sense that if you take any interval in the integers, the intersection of the interval with your orbit of squares grows like the length of the interval to the half. So it's sort of half-dimensional. And similarly, if I take the Minkowski sum of this orbit with a unit interval, then I essentially grow like half of the length of any other interval inside of R. So from the perspective of density, the squares act half-dimensionally. And indeed, this property about the sequence plus the unit interval is very, very different from the continuous setting, where the trace of t squared is all of R. So in the continuous setting, the trace t squared traces out all of R, it's full dimensional. In the discrete setting, the orbit n squared is only half dimensional. So there's very, very different geometrically going on if you try to compare the discrete and the continuous formulation. And indeed, if you're trying to prove the continuous jump counting function behaves well, you can just use change of variables and a little bit of convexity. There's no new difficulty. But of course, you can't use change of variables over the integers because of the presence of a smallest scale. There's no type of infinitesimal, so you can't possibly make this move. So this is an L2 based problem, so it makes sense to try to use the Fourier transform. And if we do this, we can very cleanly express this type of discrete average as a convolution operator, where my convolution kernel is given by Kn. Or if we use Fourier inversion, we can express this as a multiplier where my exponential sum is just given by e to the 2 pi beta n squared. So this is a Gauss sum. So contrast to the linear situation. In the quadratic situation, I have beta n squared. In the linear situation, I have beta n. And these types of multipliers are very easy to understand. When beta is much less than 1 over n, all of these numbers are trying very hard to be 1, and this multiplier tries hard to be 1. When beta is much bigger than 1 over n, this multiplier is trying very hard to be 0, sort of by summing a geometric series. So in particular, you can really understand what this multiplier is doing just by looking at the distance from beta to the 0 frequency. So this is sort of a 0 frequency multiplier. But when you're interested in the Kn hat multipliers, these Gauss sums, they're quite a bit more subtle, and they require the circle method to fully analyze. So the circle method is a technique from analytic number theory, but it's largely probabilistic. Basically, this type of average is an average of n mean zero pairwise independent random variables. So you might expect a generic power savings. If you had honest independence, you might expect n to the negative a half. And these are just pairwise independent, so maybe expect n to the negative epsilon. But there's an obvious obstruction to this type of reasoning, which comes from the potential correlation of the phases beta maps to n squared. So this is best showed off with an example. If I choose beta to be a third, then when I sum up this exponential sum, well, I sum up e to the negative 2 pi I 1 over 3 plus e to the negative 2 pi I 4 over 3 plus e to the negative 2 pi I 9 over 3. So that gives me a 1 plus 2 copies of e to the negative 2 pi I over 3. And every 3 n's, I just get a repetition. So even though formally speaking, I have capital N sums, there's only 3 instances of distinct behaviors because of the arithmetic structure of this 0.1/3. So even though formally speaking, I have n sums, I really only have 3 sums, and there's no hope of decay. This number is certainly bounded away from 0. But this is basically the only obstruction. So after a little bit of elementary number theory, you arrive at the following dichotomy. Namely, these Gauss sums are large and interesting whenever the frequency is n close to a rational number with an n small denominator. In this case, we say that beta is an n major arc. And unless this happens, the probabilistic intuition kicks in, and our multipliers are sort of negligible. And if you translate this information in Fourier space back to physical space, you end up with a very particular class of examples that you need to understand. So these chi-qn's, I'm taking a Ramanujan sum, e to the 2 pi a over qn is a over q and a less than q is coprime. And then I multiply this Ramanujan sum by some L1 normalized indicator function, where we think of q as being less than n over 1,000, n to the 1 over 1,000. So if this Ramanujan sum weren't there, chi q would just be some type of L1 normalized average. It's not enough to test kn against these types of L1 normalized averages. But if we just introduce these Ramanujan sums, these chi-qn's tell the whole story. So in particular, Bourgain's challenge was to estimate the jump counting function of these convolution operators applied to superpositions of these arithmetically averaged of your arithmetically averaged function. So for each qi that's about q, I average my function f over an interval of length qi to the 100, weighted by this Ramanujan sum. So if this Ramanujan sum CQ weren't there, this would just be a Lebesgue average. And I'd be interested in understanding oscillation of averages. With these Ramanujan sums, there's some oscillation that's built in. And I'm interested in understanding the extent to which these FQIs superpose. And in particular, I really want to avoid using the triangle inequality. I want to look for destructive interference between the FQIs. So at the single level, this isn't so hard to show that if I have these FQIs, where I average my F over these L1 normalized indicator functions that have been modulated a little bit, then as long as n is sufficiently big, I get a lot of decay at the single scale level. So we have a uniform bound. Each individual average makes this type of superposition small. And I want to show that the oscillation of all these averages, the jump counting function of all these averages is small. So if you look at the top line, each function inside the bracket of nt is small. Each of these are uniformly small. And I want to show that they don't oscillate too much. So they're all, for every n, this convolution of kn is like q to the negative a half times the L2 bound. And what Bourgain did was he showed that even when you introduce this measurement of oscillation, you still get a very strong rate of decay. So Bourgain first proved this result with a log q squared. You can do a little bit better. The numerology, though, isn't too important. The key takeaway from this is that I have some negative power of q, even when I take into account the oscillation. So the scheme kind of presents, in seeking to try to prove pointwise convergence of these averages that Bourgain considered, there's sort of a rough scheme. Use transference to reduce the problem to proving a quantitative estimate involving convolution operators on the integers. You use the Fourier transform and the circle method to capture the analytic heart of the operator. And then you estimate the jump counting function. And this is quite straightforward in L2, where all the quotes that I've used can be quantified by Plancherel, but this still works to some extent on an LP as well. So onto the problem at hand. Our job was to prove convergence of these Bn functions, and we went through a similar transference mechanism as Bourgain. So in particular, if we let Mn denote the pertaining bilinear averaging operators over the integers, we're after a jump counting estimate for these bilinear averaging operators. And the representative case is L2 cross L2 to L1. So again, we have L2 cross L2 to L1. So Plancherel's theorem isn't useful. We have no analog of Plancherel's theorem to implement the circle method naively. So just to get started, we needed to use some very subtle additive combinatorics of Sarah Palouse and Sean Prendeville. So I'll explain the statement. Suppose that f and g are sub-indicator functions. They live underneath an interval of length n squared. So the greatest possible value that mn of fg could obtain is itself n squared. If f and g are constant, for instance, mn of fg will have L1 norm like n squared. So the inverse, what Sarah and Sean did is as follows. They said, suppose that you're not n squared, but you're logarithmically close to n squared. Well, the conclusion is that your functions must have a lot of additive structure, in that if you average f over cyclic over a coset mod qz, where q isn't too big, then the resulting function still has large size. So quantitatively, if my bilinear average is at least log the negative O of 1n, as big as maximal, then there's some integer q less than log O of 1 to the n, so that if I average f over long intervals with gap size q, so by long I mean n times log n to the negative O of 1, then this resulting average, it's not as big as it can be, it's not n squared, but it's only logarithmically far away from n squared. So this is a very, very strong inverse theorem. The only way that your bilinear averages can be big is if f carries is large on an arithmetic progression. So after some work, you can reformulate the Palouse theory as follows. So suppose that f and g are bounded by the indicator of an interval of length n squared, and the bilinear average is nearly maximal. Well, the conclusion is that there's some q that's not too big, so that f hat has large Fourier coefficients near z mod q, and simultaneously g hat has large Fourier coefficients near z mod q. And what I mean by near is in terms of scaling. We're shifting f linearly, so near means 1 over n, and I shift g quadratically, so near means 1 over n squared. So with this above inverse theorem, we introduced an approximation argument designed to sort of extract the analytic heart of our problem that used tools from discrete harmonic analysis, namely Ionesco-Wenger theory. We used some Gowers type Harmonic separation arguments. And then we also needed the Vinogradov mean value theorem. We needed some hard analytic number theoretic estimate. But once you've made these approximations, you end up in a situation that's not so different from Bourgain. So in the previous situation, when we were doing Bourgain's theorem, we were looking at convolving single scale objects with these FQ functions, which are these weighted averages. In the bilinear setting, we're looking at two weighted averaged functions whose least common multiple isn't too big. And we're looking at what our bilinear averages does to these two types of functions, which are again arithmetically compatible. So if you start with what Sarah and Sean did, and you apply the three big tools that I mentioned, namely Ionescu-Wenger theory, Gowers type separation arguments, and the Vinogradov mean value theorem, you end up with some gain at the single scale level. So for every n bigger than q to the 1,000, whenever q1 and q2 have a small enough least common multiple, I have uniform control over these bilinear averages. So whenever I average f over intervals of length q to the 100 and g over intervals of length q to the 100, weighted arithmetically, I have a great deal of the destructive interference that I can superpose these averages and I still get cancellation. And what we needed to do was we needed to formulate a jump counting version of this uniform control. So this is sort of superficially similar to Bourgain. For every r bigger than 2, there's some positive C naught, so that whenever I'm adding superpositions of these bilinear functions whose least common multiple is about q, I get a little bit of gain. So Toulouse-Prendiville theory plus these other three ingredients gives you a uniform bound. All of these MNs are individually small. And what we needed to do was to prove that the oscillation stays uniformly small. So there was some new additive combinatorial input that we needed beyond the three pieces of previous ingredients. And this is a nonlinear Roth theorem in the cyclic subgroup setting. So the statement is as follows. Suppose that delta is positive, that P is a pretty big prime, and that Q is a power of P. Then whenever A is a subset of Z mod Q, which is relative density bigger than this delta, then A necessarily contains a nonlinear 3AP, x minus n squared. So this was the new additive combinatorial ingredient that we needed to prove this oscillation estimate. We needed generic chaining from Banach space geometry. And we also needed some oscillatory integral techniques over the p-adics. We needed to understand the percentage of time that polynomials can concentrate near single values over the p-adics. And because of these sort of different techniques that were needed, we worked both in physical space using combinatorics and using Fourier space using harmonic analysis. So the argument went back and forth between physical space and Fourier space. So the goal now is to upgrade this type of convergence to higher degrees of multilinearity. So using more refined work of Toulouse, joint with Mariusz Mirek, Sarah, and Jim Wright, our goal is to prove the following convergence statement, that whenever you have m-bounded functions, m polynomials with distinct degrees, and m commuting transformation, these averages converge pointwise almost everywhere. And this is a bit of a typo. As of earlier this year, we have the result when the PIs are distinct monomials and there's only one transformation. So when T1 is T2 all the way up to Tm, and all the PIs are monomials that are distinct, we have a convergence result. And I can't do this, but I'm sort of optimistic that my collaborator, Jim Wright, has enough p-adic analysis that he'll be able to upgrade this from distinct monomials to polynomials of distinct degree. Regarding polynomials of the same degrees, the model problem concerns pointwise convergence of Tn squared f, T2n squared g. So Bourgain handled a similar problem when you replace n squared with n and 2n squared with 2n. Bourgain proved pointwise convergence of these averages. But when you introduce this half-dimensional behavior that comes from the squares, the problem changes dramatically. So understanding this problem will require all the ideas that I did with Terry and Mariusz, plus additional time frequency input. The other major open problem, which I think is even more compelling maybe, concerns pointwise convergence of the trilinear averages, TNF1, T2NF2, T3NF3, whenever F1 and F2 and F3 are bounded. And this problem will require not just Fourier analysis, there'll need to be some higher order Fourier analysis. This bilinear average, the family of these bilinear averages admits a very wide class of symmetries, which makes studying these averages very, very challenging. And in particular, pointwise convergence of these averages will go a long way to proving pointwise convergence of the trilinear Hilbert transform, which is like the major open problem of the field. So I think these averages are, pointwise convergence of these averages is a long-term problem, but it's on the radar now. And I'll stop there.
Question?
Ben, can I ask you something?
Yeah.
So, in the case of mean convergence, when we assume T-weak mixing single transformation, we have major simplifications. In your case, assuming T is weak mixing gives any simplification at all for the Tn squared?
So for return times theorems, yes. If you're trying to prove a joint combination of Bourgain's polynomial ergodic theorem and the return times theorem, then we
No, just the result that you wrote, the nn square.
No, it's if you're interested in return times phenomena, then it's useful. But for these ones, no.
So actually nn square can be reduced to weak mixing. And so it is as hard because you have, when you do Hilbert splitting, there are 4 expressions.
No, but for pointwise convergence, you cannot.
The pointwise convergence for n square in general is reducible through Hilbert splitting to weak mixing.
No.
Just split in 4 expressions.
But you have to own the orthogonal component.
No, that's the point.
This is orthogonal. If it's not true that if you prove this, the Tn square for weakly mixing,
No, it's morally.
you have it.
I don't say if, but morally, it's really the level of difficulty is that of weak mixing. That's what it is.
If you could show that the characteristic factor is the Kronecker, then I agree with you. But proving the statement for weak mixing does not allow you to show that the characteristic factor is the Kronecker.
To summarize, I don't believe it's easier for weak mixing.
Yeah, okay, yeah. In our case, it was.
I understand.
So in the mean convergence case, so why not in the, yeah, that's what. Okay, and you didn't say anything about the TNSN, two commuting same. Is this radar now?
So I think that there's a similar type. So this is back of the envelope work here, but I think that in the same way that in Bourgain's double recurrence argument, you can assume that one of the functions is orthogonal to the Kronecker factor. I think that in the TN-SN case, you can make a similar assumption that one of the functions doesn't correlate with eigenfunctions very well.
Oh, no, that's exactly the delicate point. I think Nikos will.
You have
really-
TS inverse invariant function.
Yeah, for T and S, the
Anyway,
complexity
so
factor
this
is
is-
beyond Kronecker. That's why it's harder. It's definitely.
Okay.
I think this is, I'm plagiarizing an idea from Sarah, who sort of explained this to me. I don't know if I'm doing her credit. This is, so the harmonic analysis model, doesn't take this reduction into account. It's still sort of the harmonic analysis model, the most naive one, doesn't use this type of poor correlation with eigenfunctions. But I think Sarah had an argument that said that this was enough to do, that you could assume that at least one of your functions doesn't correlate with eigenfunctions for the rotation.
I think she's up. She can correct you.
If she's here, she can do this more justice than I can.
If she's on.
It's formally. So you see,
Okay.
Ben,
Thank you, Ben.
even for norm convergence, you have to work harder than that. Okay. So if for norm convergence it's not enough to assume absence of correlation with Kronecker, then surely for pointwise it should be hard.
Okay.
More questions? Okay, let's then. And again.